Pluto's way will undoubtedly cause issues from the start. Pluto's circle meets that of another planet. Pluto, the secretive and minute planet situated in the farthest corners of our planetary group, has turned into a hotly debated issue in cosmology. Late updates suggest a potential impact with Neptune, raising alarms among researchers and space enthusiasts. Notable figures such as Neil deGrasse Tyson and Michio Kaku have expressed concerns regarding the potential consequences of this heavenly encounter. But how did Pluto end up on a collision course with Neptune? And what could this cosmic conflict mean for Earth? Join us as we explore the details of how a massive event with Neptune could have occurred and why scientists are disturbed by this cosmic anomaly. Pluto, once celebrated as a full-fledged planet, underwent a dramatic reclassification as a dwarf planet, largely because of its eccentric orbit. Despite this demotion, Pluto continues to fascinate and ignite interest within the astronomical community. Recent warnings from prominent scientists such as Neil deGrasse Tyson and Michio Kaku have suggested that Pluto's path could intersect with Neptune's, posing a potential risk of collision with serious implications for our planet. Pluto's journey around the Sun is extraordinary due to its unique characteristics. Its orbit is particularly lengthy, requiring a massive 248 years to complete. Since its discovery in 1930, Pluto has not yet completed a full revolution around the Sun. What makes Pluto even more captivating is the highly elliptical shape of its orbit, a stark contrast to the nearly circular orbits of the major planets. Furthermore, Pluto's orbit is tilted at an angle of 17 degrees relative to the ecliptic plane, resulting in a steeper incline compared to the paths of other planets. This combination of inclination and its elongated orbit adds complexity to its movement. An exceptional aspect of Pluto's orbit is its repeated intersection with Neptune's orbit every few centuries. Pluto's path brings it closer to the Sun than Neptune, which challenges what we might expect from their relative positions in the solar system. Further investigation reveals that Pluto's orbit is far from a perfect circle. Instead, it follows an elliptical or oval path, meaning its distance from the Sun varies significantly throughout its orbit. At its closest point, Pluto comes about 30 astronomical units from the Sun, but at its farthest, it stretches to over 49 astronomical units, nearly double the distance of Neptune from the Sun. Additionally, Pluto's orbit is inclined at an angle to the orbits of other planets, adding another layer of complexity to its relationship with Neptune. This inclination plays a crucial role in how Pluto and Neptune interact. When their orbits intersect, their gravitational forces tug at one another, gradually altering their trajectories. This dynamic between Pluto and Neptune highlights the interconnected nature of the solar system, with each planet exerting gravitational forces that influence the movements of others. Over the years, technological advancements in observational instruments have allowed astronomers to track Pluto's movement with greater precision. This has led to a better understanding of its orbit and its potential impact on the overall stability of the outer solar system. Although the likelihood of a direct collision between Pluto and Neptune remains low, the possibility is still under scrutiny. Ongoing monitoring continues as the potential consequences of such a collision could be dramatic. Despite Pluto's small size and distant location, it continues to be a subject of interest for scientists and space enthusiasts alike. A key question that arises is, why hasn't Pluto already collided with Neptune? The answer lies in the gravitational influence of other planets. From the moment Pluto was discovered, astronomers have been working to understand its path. Unlike most planets, which maintain a stable orbit along the ecliptic plane, Pluto's orbit stands out with its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit remains remarkably stable, demonstrating the intricate mechanics that govern space. Studying the interactions between Pluto, Neptune, and the Sun presents a significant challenge for astronomers. Predicting their movements requires a deep understanding of how they influence each other's trajectories. To tackle this challenge, scientists rely on principles such as asymptotic libration, scope libration, and VSOP, variations séculaires de orbites planétaires. Asymptotic libration, for instance, is essential in maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it remains at least 90 degrees away, preventing a direct collision. Scope libration ensures that when Pluto approaches Neptune or other large planets, it is positioned above their path, reducing the likelihood of an accident. The VSOP oscillation, named after scientists von Zippel, Steves, and Kaplan, explains why Pluto's orbit appears unusual yet remains stable over time. Although space seems chaotic, there are underlying patterns that help maintain order. These patterns are responsible for preventing Pluto from colliding with Neptune or significantly altering its orbit. The concept of orbital chaos, which describes how a celestial body's trajectory is highly sensitive to its initial position, is clearly demonstrated by Pluto's orbit. Even small variations in Pluto's position or velocity can have significant effects over long periods. Scientists use advanced virtual simulations to model Pluto's interactions with other bodies in space, such as Neptune, and to explore the consequences of even minor shifts in its course. In the late 1980s, these simulations provided groundbreaking insights into the stability of Pluto's orbit and its interactions with Neptune. They demonstrated that Pluto's orbit, despite its eccentricity and repeated intersections with Neptune's path, is governed by a phenomenon known as orbital resonance. Specifically, Pluto and Neptune are locked in a 2:3 resonance, meaning that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that the two celestial bodies never come close enough to collide, as their positions are always out of sync when their orbits intersect. This precise orbital resonance acts as a safeguard, preventing a catastrophic collision and maintaining harmony in the solar system. It is a testament to the remarkable balance that governs the motions of celestial bodies, even in seemingly chaotic conditions. Without this resonance, the gravitational interactions between Pluto and Neptune could destabilize their orbits, potentially leading to collisions with other celestial objects or even being ejected from the solar system altogether. Astronomers continue to study Pluto's orbit and its long-term stability using increasingly sophisticated computational models. These models take into account the gravitational influences of all the planets, as well as the effects of other forces, such as the gravitational pull from the Kuiper Belt, a region of icy bodies beyond Neptune where Pluto resides. These simulations help scientists predict potential changes in Pluto's orbit millions of years into the future. Despite the protective mechanism of orbital resonance, the possibility of external factors influencing Pluto's trajectory cannot be entirely ruled out. For example, a close encounter with a large Kuiper Belt object or the passage of a massive celestial body through the outer solar system could disrupt the delicate balance of Pluto's orbit. Such events, though rare, could have significant consequences for the solar system's dynamics. In addition to its scientific intrigue, Pluto remains a cultural and emotional symbol for many. The debate over its planetary status reignited public interest in astronomy and highlighted the ever-evolving nature of scientific understanding. Whether as a dwarf planet or a full-fledged planet, Pluto continues to captivate imaginations and spark curiosity about the mysteries of our solar system. As researchers strive to unravel the complexities of Pluto's interactions with Neptune and other celestial bodies, one thing is certain: the story of Pluto is far from over. It serves as a reminder of the dynamic and interconnected nature of the universe, where even the smallest and most distant objects play a vital role in the grand cosmic ballet. Revealed something entrancing. Regardless of the obvious steadiness of Pluto's orbit, it can still act unpredictably. A minuscule modification in Pluto's starting position or speed could lead to massive changes in its orbit over time. However, even with these uncertainties, Pluto's orbit remains stable for billions of years, suggesting that despite its whimsical appearance, it follows a basic order. The unpredictability of planetary orbits, such as Pluto's, makes it difficult to predict long-term changes with certainty. These models require extremely precise initial conditions, as even small errors in data can produce vastly different outcomes, making accurate predictions incredibly challenging. Understanding Pluto's orbit is essential, especially when considering the potential for a future collision with Neptune. This information contributes to a broader understanding of how our solar system operates. Pluto's orbit serves as an example of how seemingly chaotic paths can ultimately reach a balance, guided by the forces of gravity and motion. It is crucial to continue observing and studying these celestial mechanics to gain a better understanding of our place in the universe. Pluto's orbit offers a perfect illustration of the unpredictable nature of space. Unlike other planets, Pluto's elliptical orbit leads to unpredictable encounters with Neptune. This irregular movement makes it challenging to predict the long-term dynamics of the system. However, gravitational forces play a critical role in preventing Pluto and Neptune from colliding. Gravity, a force that attracts objects to each other, ensures that despite their intersecting orbits, the two bodies remain separate most of the time. These interactions reflect the delicate balance of forces at work in space. The possibility of a collision between Pluto and Neptune, while unlikely, would be a monumental event with significant consequences. Such an event would drastically alter our understanding of the solar system. Despite significant advancements in space exploration, Pluto's orbit serves as a reminder of the many uncertainties that still exist. Scientists continue to study Pluto's path to better understand how larger planets influence its movement. This knowledge is crucial for understanding the complex relationships between celestial bodies and how their movements affect one another. Despite the unusual nature of Pluto's orbit, some of the world's leading scientists like Neil deGrasse Tyson have speculated that Pluto may one day collide with Neptune. Tyson, a prominent astrophysicist, views Pluto's reclassification as a dwarf planet as an essential step, emphasizing the importance of continued exploration and study. He believes that Pluto's strange orbit highlights how much there is still to learn about space and the forces at work within it. According to Tyson, the mysteries of space make its study so captivating, and he encourages others to engage with the fascinating complexities of celestial mechanics. Tyson, along with other experts, is concerned about the potential dangers posed by Pluto's unusual path. If a collision between Pluto and Neptune were to occur, it could have devastating implications for our solar system. The release of energy from such an event would be enormous, and the debris scattered throughout space could have far-reaching effects, potentially even impacting other planets and moons. Neptune itself would be affected, and its orbit could be altered, further complicating the dynamics of the outer solar system. Renowned theoretical physicist Michio Kaku, known for his work in string theory, also provides valuable insights into space exploration. Kaku believes that studying phenomena like Pluto's orbit is crucial for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that investigating Pluto's interactions with Neptune can help scientists navigate future space missions more safely. Kaku also emphasizes the importance of understanding gravitational forces in the context of space exploration, as they have the potential to shape the future of how we explore distant worlds. Kaku's work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could offer valuable data that would contribute to our understanding of gravity and spacetime, key to string theory. Although such an event would not directly impact Earth, it could provide a unique opportunity to study the behavior of fundamental forces in extreme conditions. As scientists continue to explore the depths of space, the unpredictability of planetary interactions becomes more apparent. The study of celestial dynamics, such as the intricate gravitational relationship between Pluto and Neptune, offers significant insights into the fundamental laws of the universe. By continuing to monitor and study these phenomena, we move closer to understanding the vast and complex nature of the universe. The gravitational dance between Pluto and Neptune highlights how even distant planets can influence each other. These celestial bodies exert gravitational forces that, over long periods, can subtly yet significantly shape their orbits. While a direct collision remains unlikely, the possibility cannot be entirely ruled out, leading to ongoing interest and observation from the astronomical community. Scientists believe that understanding these forces may one day allow them to predict and potentially mitigate the risks posed by such cosmic events. One fascinating aspect of planetary motion is how seemingly random or chaotic interactions can lead to stable, predictable patterns. This phenomenon is particularly evident in the case of Pluto, whose orbit may appear erratic but is governed by precise gravitational forces. These forces help prevent Pluto from colliding with Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of various planets and Pluto's orbit keeps the dwarf planet in a steady yet complex trajectory. Understanding this intricate relationship is essential for advancing our knowledge of the broader solar system. As scientists continue to study the unique characteristics of Pluto's orbit, they also look toward other areas of space exploration. The study of systems like the TRAPPIST-1 system, which contains multiple Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances and, in some cases, increase the likelihood of a planet's orbit becoming unstable. Although the TRAPPIST-1 system is not currently experiencing any collisions, scientists remain vigilant, tracking the movement of planets in these crowded environments to better understand the risks and how they might evolve over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, which wander through space without being bound to a star.